Hello community, we have some beautiful new research here. Just 3 days ago, we have here the University of Illinois here in the US published here a new research paper, Graph Router, a graph-based router for LLMs. Now, you know that if we have specific tasks, specific queries, and we have LLMs at a specific price point and a specific performance that we expect, it is rather simple to build here a graph. However, it is much more interesting to build here from the graph now a graph neural network so that we can discover hidden edges or nodes or connections within a dynamic graph network. So, in the worst case, we can say, hey, let's predict future LLMs for unseen tasks. But of course, we want to have an optimization of the graph data for the LLMs that we already know of. Now, the training of a graph router in itself is not really particularly difficult, and I don't want to focus on this, but I want to show you how do we build this graph, because there are some complexity that are just beautiful. So what is the task at hand? So we start here with, we want to efficiently select some specific LLMs. Do you go with Claude? Do you go with Sonnet? Do you go with O1, with a Mini? Based on your specific task, on your requirement, given the projected performance that we can expect from those systems for your task and the anticipated computational cost, and then the price point that Microsoft is asking you. So, easy. How do we build a graph? Now we have nodes and edges. So with nodes, the researcher went here with a simple 3-type node model. So we have the models. And each and every of the models you see here, beautiful, is now a node structure. Plus, we have different tasks. We can go for a question answering task, for a summarization task, for a text generation task, for a sentiment analysis, for a dialogue system. You got the idea. And then we have specific user queries. So let's say in the question answering class, I have open domain question answer, closed domain, extractive Q&A, abstractive Q&A. So I have here a complete classification with particular queries. So this is some dense data set. And then of course we need edges. Well, couldn't be easier, no? We have the LLM nodes that connect now here to the query nodes, and we have the task nodes that connect to the query nodes. Yeah, but the beauty is we have some irregular nodes too, no? We have nodes within here a task node structure, or maybe we have some cross-reference, depending whatever the graph might show us. So, how do we build a graph now that we have the node and the edge classification done? Now we just need the data. And of course, on our edges, we have information about the price point, about the latency or the task execution in total. So you have a lot of information that you could put into your graph representation. If you want to learn more about edges here and the power of graphs, I have this video for you. If you want to see a link prediction, is this video. If you want to go with here a computer model here, I would say PyG for torch geometric data is really beautiful. I'll show you here the definitions. Or, and this is what we will look at a little bit later on in about 2 minutes time, if we have a graph, how we go to a graph machine learning computational graph structure. But for the moment, let me focus here on PyG S-BERT. So we have heterogeneous graph using here sentence transformer. Great. So here we are, and now the task is easy, no? How to build a graph? We need a graph representation. And a graph from a little grasshopper is a data structure where the nodes, this is our task, our queries, and our LLMs, are connected by those edges to represent relationships, but not physical distances. We have no metric here in this space. So, edges between nodes are defined based on how the entities interact. The task relates to a specific query, or the LLM generates a response for a specific query. And we have, of course, the edge weights, or the attributes here of the edges, and they represent characteristic data, like the performance or the cost data, whatever you want you put here in the edge weight structure. But you remember the weights do not respond here also to Euclidean distances, but everything is here just on a relational basis. So what edges do we have? As I told you, we have task query edges. So if you have a task node for mathematical reasoning and a specific user query like what is the sum of 35 and 58, then the edge is created exactly between those nodes in the training data. And there's no complex add feature data, but you could just assign a binary value you represent that a query belongs to this task. So you see, we can start really easy. Next, we have the LLM query edges. Here you can put your data about performance and cost. You can calculate these values based on your historical data, or you just look it up, or you have it in your training data already. And then it is rather easy, no? And I show you here PyTorch geometric examples here, import torch geometric here. We have now our tensor structure for the task nodes and a tensor structure for the query nodes and a tensor structure for the LLM nodes. We have the embeddings, we combine them, we have the edges, and we create our graph data here. You see, just some lines of code. But you might say, hey, wait a minute, what do you mean we have the task embeddings? Where does the embeddings come from? Okay, no problem at all. Embeddings. Embeddings are simply used to represent nodes and edges in a way that would allow here multiple models to learn relationships and to learn those relationships efficiently. Let's say the task node embeddings. Now, these are generated using here an LLM, and let's say we have GPT-4 to create now a descriptive text for each specific task. GPT-4 can do this easily. And those descriptions are then passed through a pre-trained language model, but a very specific one, like here BERT, a sentence transformer model, to produce task embeddings. So this means we just create a new vector in a vector space that we also have to create. So, example, the task question answering here is described by GPT-4, and then the resulting text, maybe each sentence, or maybe you take a complete paragraph, or you take the complete text, and you just embed it using here the sentence transformer BERT in a vector space. Let's go to the query node embeddings. It is rather similar. Embeddings using here the same pre-trained BERT model. So example, what is the capital of France is passed through BERT to generate a query embedding. And we get a new vector. And then the LLM node embedding, now you know it. Descriptive embeddings are generated using here a prompt to obtain details about the LLM's capabilities. So GPT-4 is prompted to generate a description of O1 Mini, which is interesting in itself. And then this textual description generated by an AI is now the input into a sentence transformer model, and this sentence transformer model outputs here a specific vector representation in a specific created vector space, and this is what we call an embedding of this particular information. So you see, we have quite a lot of LLMs interacting with other LLMs, passing information through sentence transformer just to create the initial embedding of the nodes. And then we are now really ready to go and have here a look, for example, at this video that I have 2 years old. Never mind, it's still actual. How we go here from BERT in sentences to a vector representation with a bidirectional encoder stack. And I have here 7 videos, so you can have a deep dive in whatever computer code you prefer. You can go here with Keras. I have all the other languages available. So this means now we understand that the way to come now from our embeddings here, there's quite some complexity, because the vector space, the quality of the vector space is important. If you just go and buy some vector space, you cannot be sure that your specific data are within this vector space. You know, simple, or language. Maybe you would have the French version and you can't buy an English vector store, no? Or you have a topic-specific vector store. So you see, there are a lot of complexities there, not even mentioned, but it is, of course, you have to prepare, you have to go through all these steps. But sometimes you do not find it anymore. But there lies here massive problems. So now we have a graph. Isn't it beautiful? We have here PyG created here a graph, or whatever software package you want. And now this graph is here. But now, as I told you, we want to make predictions, no? We want to have insight into the encoded information here to say if now a new query comes along that was not in the training data set, so what model is it, at what price point, at what complexity level? Or imagine we have now a new LLM coming out, and we have now a description by GPT-4 describing now O2 model, then theoretically in the graph, based on the similarity in the vector space of the description that was generated by GPT-4 on O2, we can build, let's take network X, the simplest software package here, a graph structure where we use here the similarity in the vector space to optimize here the graph for new unseen data, and we can argue on semantic similarities in the vector space. So you see, the logic behind this is maybe not as trivial as it may sound. So our step now is to go from a graph to a graph neural network, a GNN. I already have a video on this. It's so beautiful, you know, from graph data to graph machine learning, how to build a computational graph. You have different message passing aggregation mathematical function. I explain everything in this video if you want to build it. So you see, for my little green grasshoppers here, embeddings allow us to convert now high-dimensional data, either text, task, queries, into lower-dimensional vector representation if we use, for example, UMAP. And these vectors encode semantic information about the input in a way that is easy for machine learning models like our graph neural networks to process. Oh yeah, I forgot to mention that here, if you really go to a lower dimensional vector representation, the mathematics behind these operations to come down to lower mathematical space dimension, but incorporate the complexity of the original information, this is not an easy task, and I have, I think, about 10 videos on UMAP. Great. So, for example, instead of representing a task query as a raw text, embeddings condense the information into a fixed size vector. We already talked about this, capturing essential features such as the relationship, queries, task difficulty, or capabilities. And those embeddings also enable inductive learning. So you see, wherever we are faced with embeddings. We have to find simpler representation in simpler vector spaces to be able to do anything at all. Now, the graph router, as in the publication, this brand new publication just 3 days ago, uses also BERT-based embeddings here for the node representation. Bidirectional encoder representation, yes, I think I have 50 videos on sentence transformers, so no problem at all. So for my green grasshoppers, we have the task node embeddings, the query node embeddings, and the LLM node embeddings. The task node generated from the task description using BERT, generated from queries using BERT, generated from LLM description using BERT after GPT-4 came up with new descriptive details. As you see, the interplay of the complexity is now amazing. And I think sometimes we forget that we start here with a simple complexity in our vector space, in our sentence transformers, in our bidirectional encoders, in our next step, in our compression here of mathematical dimensions, in our next complexity if we have a semantic description, and in the next complexity if we do projections on graph neural network or message passing, or we want to have a link prediction. We should be aware that on all levels, errors can happen. But let's look here at a complexity that is so huge we hardly see this complexity. And there's now the second paper, and this is a beautiful paper here beginning of October 2024, Auto Machine Learning Agents. Now this is the real stuff here. Case Korea, beautiful deep auto. A multi-agent LLM framework for full pipeline auto machine learning. We have everything that we are dreaming of. Not one agent, but a complete multi-agent scenario. Multiple LLM frameworks are employed here to build for us the complete pipeline for the complete end-to-end exercise with automated machine learning. It couldn't get more beautiful. What do you think about this? So yeah, we have here this visualization with the little sheeps, but since this will be an economic activity that will bring in hundreds of billions of dollars, I do not go with the sheeps. And even if the sheeps multiply and it becomes a little bit more interesting, no, let's choose something else. Let's go with this here. This is here a simple visualization. So what we have the time horizon, and they go from end to end. And never mind what is the absolute time, we're just looking here at how big are the chunks for the single processes. Now, first we start with a prompt parsing, then we have a request verification, and then we have retrieval and planning. And as you can see, wow, this is a huge chunk. And then we have plan execution, also massive. Then we have a little bit of an execution verification and a selection and summarization here in these two colors. And then we have code generation. And the first time I saw this, I said, hey, this is interesting. So in an end-to-end real code generation is about a third. No, this dark blue here. And those two are now the new emerging focus points in AI. So let's make it even easier. I call this coding. I call this here plan execution. And this here, retrieval and planning. So 3 simple tasks in a complete automated machine learning pipeline generated only by multi-agent AI systems. Let's have a look what is retrieve and plan according to the authors. Critical phase in the auto machine learning agent framework, multi-agent framework, where the system generates multiple plans to solve here the task. You know, that's beautiful because we just not go with the highest probability task, but we say, hey, we want a set of options for our task, and then we want to have a detailed analysis of the risks, for example. So we have at first parsing here the user requirement, utilizing the user's instruction that are at the beginning of everything to understand the task at hand really in all details. What is it that the user wants? Where do we start? What is our initial condition? What data do we have? What access to what systems do we have? What computer simulation can we call independently? Do we have access to the internet? Do we have access to different databases? Everything, you have to think about this and build here at first a plan. Now, you know, in my last video where we're talking here about queries, user queries with a high complexity, like a complexity 8 out of 10, if we try to decompose those in 2-level complexities, this is not really what might be working, but never mind, let's go on. The next stop here, retrieve. So we have to retrieve external knowledge, accessing external data, up-to-date data relevant to the task. Beautiful. And then we have generating multiple plans. So we're creating now a set of diverse end-to-end plans from the data retrieval to the complete model deployment phase based on the internal knowledge and everything we can have access to with our data. So what does this step do? Simply ensures that the framework considers a wide array of possible solutions, enhancing the chances of finding the most optimal one that satisfies here my user requirements. Sounds easy, but as you see, it is almost as powerful as the complete code generation. Second part now is the plan execution. Let's have a look at this. What is it? Plan execution, according to the author of this beautiful study, refers to the stage where the generated plans from the planning phase are now executed by specialized agents. Now we have our multi-agent scenario, but be careful because there's a critical distinction. So 4 points. We start with point number 1, plan decomposition. The same what I just told you here about a C8 of 10 complexity. Can we decompose those complex tasks at all? But let's assume, yes, let's have a green light. Due to the complexity of end-to-end plans covering the entire auto machine learning pipeline, the plans are broken down into smaller, manageable subtasks. And then each plan is decomposed into subtasks specific to the agent's role and the expertise. This is also in one of my last videos I was talking about the super agent. This here is exactly, if you want, an implementation of the super agent. You say, hey, I have 20 agents and I have now a specific subtask. And now I have to find the correct subtask for an agent where the agent can give me back, I don't know, a 90% confidence level. So data-related tasks are assigned, of course, to the data agent, doing all the data management, and the model-related tasks are assigned to the model agent. Now, this is great because this decomposition allows you a reduction in the complexity. It's faster, it's less expensive, and this allows agents to focus on their specialized tasks that they have been trained on, improving efficiency and effectiveness. Great. Second step, prompting-based plan execution. Now, as I told you, there's one critical element. We are not really sending the data off to the real world execution, but this is here a computer simulated execution. It would be much too expensive to really connect to all these agents and really run this at this level already. We will only do this here much later in the coding phase when we will generate the code for this. We are here still in the optimization phase and we work here with computer models that simulate the performance of agent for a particular task, for a particular code generation. So you see, we have another complexity. How good are the agents to simulate this? Is this real? The real thing? Let's say everything works out fine, beautiful. So execution of the assigned subtask without actually running the code. This means they act as if they were performing the task to provide expected outcomes based on their knowledge. If your computer simulation of the knowledge and the performance of the AI agent varies just, 10 to 20%, you can have now maybe a plan chosen later on that is not actually the best plan to solve this task. So we have the data agent's role, handles tasks like data retrieval, data pre-processing, data augmentation, and data analysis. And the model agent's role takes insight from the data agent to inform here the model selection and the hyperparameter optimization. This now is exactly what I showed you at the beginning of this video. This is now exactly that the model agent says, hey, I have access to, let's say, 200 vision language model on, let's say, Hugging Face to be easy. Okay, so I have a specific task. I know now from 200 models, I have their description. I know their performance data on standardized benchmark data. Maybe I have my own test for my own domain-specific knowledge of those 200 LLMs or vision language model or whatever. And I know if I have to fine-tune them, I have to choose a particular hyperparameter optimization, a particular LoRa configuration. Maybe I choose multiple adapters that I want to use. This model must know all the real performance data of the real agent in this computer simulation to anticipate here the performance. Step number 3, you execute all this computer simulation, and then step number 4, you aggregate all these results together. Everything is collected, everything is brought in, and now our artificial intelligence can now come up maybe and decide, okay, but before there's the decision we have here, you see this little orange and red here, so we have the execution verification. So this is just a step to be extra careful. We say, hey, let's verify this before we really send it off here. Okay, so this is here this 1.04. So this is here this kind of an orange indicator. I don't know if you see it here on your screen. Great. And then we just have selection summarization, and then we come to the code generation. So you see those two parts are a massive amount here of time that the system will spend on. And please note that coding is not anymore, or maybe is on the third place for the importance in multi-agent systems. So this plan execution is about breaking down complex plans into specialized subtasks, and the agents that we will choose can be simulated in their performance and in their cost structure and in their time structure to gather expected outcomes without incurring here high computational cost of running them in real time for hours and hours and hours. So important to know here the performance data and the cost data of all agents that you have access to. if you look at this is time, but time is not money, no? What about the real cost? And the authors did here a cost presentation, which is beautiful. Thank you for doing this. And you immediately see our retrieval becomes now almost insignificant if you only look here at the money. It's so cheap. But plan execution double here in size if you want. And we have a complete new body here because this is a short time interval, but this is really, really costly. So what is this selection and summary? And you know what? Coding is now just a little bit. Retrieval is on the one side of the spectrum, is almost pushed to the border. And coding is also pushed to the other side of the border. And those retrieval and coding are not anymore that important as it was, 2 years ago. But you see now, for value, those are the elements that you should focus on. So let's do this. Let's go now for this select. What is it? Selection and summarization. This involves choosing the best plan based on the simulated execution result and preparing now this best plan in detail for the real-world implementation in the coding phase. Sounds easy, no? So let's start with the execution verification. The agent manager verifies the execution results from all the agents to ensure that they all meet here the user requirement. And if an agent results do not satisfy these requirements, the framework may revise the plan or adjust the parameters, maybe it goes back. Then we have the selection of the best plan. And now it is the responsibility of the agent manager to select the most promising plan that aligns with your goals, with your price point, with your time constraint, in your knowledge domain, whatever you have. This involves comparing expected performance metric, model suitability, and the complete compliance with any specified constraints. Great. Then, next step is summarization and instruction generation. So the selected plan is now summarized into a set of actionable instruction. Remember, this is some LLM doing all of this in our agent. So it depends here on the complexity level that the agent, and therefore our LLM or our VLM, is doing to do this. Find the real perfect set of actionable instruction for a specific configuration of the system. So includes detail like the chosen data set and any pre-processing steps. Hey, wait a minute. Hey. Then we have a selected model architecture and a hyperparameter, all the deployment requirements and the target platforms. Maybe you choose Google, maybe you choose Amazon, whatever. And then all those instructions are formatted to guide now the next agent that will take over here, the operational agent, in the next phase. And this next phase is here, our coding phase. And this made me thinking, why are the global players so interested now in this? Because, coding is not important anymore now that we have here all our code LLMs and whatever. Why should we as humans care at all about coding? Why should we as humans care at all about how the system retrieves information? We have AI systems for this, no? The real intelligence now is here in this middle sector. Look at where the money, the value is. 80% are just these twos. So, I have now a simple question for you. Would a Microsoft-owned model that makes notice their clear decision have a positive inclination towards an operational Microsoft-owned LLM operated on a Microsoft platform for the cloud compute, for example, and choose Microsoft-specific parameters, hyperparameters, for a perfect Microsoft-generated AI result that then you can further integrate on your Microsoft-empowered applications like Word or email or whatever you have? You see, can you build here an ecosystem like Apple? Guess what company is trying to do this right now? So you see, this level of aggregation of retrieval, coding, planning, reduce the complexity, find the right configuration of the system, select the right path. This is now the edge of research where all the global corporations are interested in. Not really in coding, not really in retrieval, but here where the value lies. Just to clarify that we are talking now about constraint-free settings and constraint-aware settings. What is this? Give you an example. I have a prompt. Hey, I need a very accurate model to classify, hey, wait a minute, images in the butterfly image classification data, the data set has been uploaded. So I just say, hey, I need a very accurate model. And I will show you why I introduce here constraint-aware settings. Here I say, hey, I want here to transfer learning from a pre-trained ResNet 50 model, and I want here accuracy of at least 95% on the test plate and provide the final trained model. So the more specifications you have, the more constraint-aware your settings are, that you tell the system what it really needs. You know what happens? Interesting. You notice here on top, the constraint-free, we just had a look at this, but this here, the bottom is now new, constraint-aware. You know what happened here in the selection and the summarization? This will become, for the money, the absolute dominant factor. Because you specified so many parameters, suddenly the optimization problem is not that easy, like here, where we had the primary intelligence into the plan execution. But now all of this goes now in selection and summarization. And you see in both cases, coding is here at the border. Coding is also here, pushed to the border, pushed to the side. So careful where you will focus here your attention, your time, and your money on, because it looks like here, looking here at the latest research paper, that we have a new research topic. And this is to find the right system configuration and look at what we have to invest here before we even enter to write some operational code. I hope you enjoyed it. I hope you had some insight. I hope you found it interesting. And it would be great to see you in my next video.